The first great AI war was fought on screens. Chat bots, search engines, image generators, coding assistants, cloud platform. The prize was information. Who could answer the question? Who could write the code? Who could generate the picture? Who could own the interface between the user and the internet? That war is still going. But a second war is beginning. This one will not stay inside a browser. It will move through warehouses, factories, roads, hospitals, farms, construction sites, stores, ports, homes. The next battle is about artificial intelligence that can see the world, understand the world, and act inside it. The industry calls this physical AI. The phrase sounds simple. The consequences are not. Digital AI produces information. Physical AI changes reality. A language model can recommend how to stack a pallet. A physical AI system can move the boxes. A chatbot can explain how to inspect a factory. A robot can walk through the facility, find the damaged part, and send the report. A software agent can schedule a delivery. An autonomous machine can load the truck. The difference is the body. One AI receives cameras, sensors, wheels, arms, hands, motors, and physical authority, and the possible market extends from knowledge work into physical labor. That market is enormous. The global economy is not made only from emails, documents, and websites. It is made from lifting, moving, assembling, harvesting, cleaning, delivering, repairing, inspecting, building, and caring. Physical AI is the attempt to make those activities programmable. This is why the next technology war could be measured in trillions of dollars. Not because one humanoid robot will suddenly replace every worker, because an entire new computing stack is being built for machines that operate in the real world. The robot is only the visible part. Underneath it sits a much larger battlefield, eyed by chips, edge computer, foundation models, world models, simulation engines, synthetic data, robot operating systems, motion planning, sensors, actuators, hands, batteries, manufacturing, fleet management, remote operation, safety systems, cloud infrastructure, identity, cybersecurity, financing, insurance, maintenance, skill marketplaces. Every layer can produce a powerful company. Every layer can become a gatekeeper. Every major technology player wants a position before the market settles. NVIDIA wants to provide the computing platform. Google DeepMind wants to provide general intelligence for robots. Tesla wants to combine AI, manufacturing, batteries, vehicles, and humanoids in one vertically integrated system. Amazon wants to turn the world's largest commercial robot fleet into a logistics advantage. Boston Dynamics and Hyundai want to convert decades of robotic engineering into industrial deployment. Figure wants to build a general humanoid platform and collect real-world work data. Chinese companies want to use manufacturing scale, component supply chains, and a large domestic market to push costs down quickly. Industrial automation giants want to protect their customer relationships. Cloud companies want every robot connected to their infrastructure. Startups want to become the operating system before incumbents move fast enough. This is not one product category. It is a fight to control the physical layer of the economy. The company that wins does not need to own every robot. It may own the intelligence used by every robot, or the simulation environment where robots learn, or the chips they all require, or the marketplace where companies buy robots' skills, or the fleet software that decides which machine receives the next task. The history of technology shows why this matters. The most valuable company in personal computing was not always the company assembling the most computers. Operating systems captured power. In smartphones, the App Store became more valuable than many phone components. In cloud computing, the platform captured spending that once went to hardware vendors and data centers. In artificial intelligence, chip platforms and cloud providers gained power because every model needed infrastructure. Physical AI can create the same layers again, but this time the software controls machines. The winner can influence not only information but production. This is the first reason the war is so important. Physical AI is not simply another robotics cycle. Robotics has existed for decades. Factories already contain millions of industrial robots. The International Federation of Robotics reported that the million industrial robots were installed globally in Ardingars, more than double the level 10 years earlier. Asia accounted for most new installations. The robot economy did not begin with humanoids. It began with repetitive machines performing predictable work. The old robot was powerful because the environment was controlled. A car body arrived in the same position. The arm repeated the same weld. The movement was programmed. The robot did not need to understand the factory. Engineers made the factory understandable to the robot. Physical AI changes that relationship. Instead of forcing the world to become perfectly predictable, companies are trying to make the machine more adaptive. The robot sees an object in a new position, recognizes it, plans a movement, adjusts grip, recovers when the first attempt fails, understands a spoken instruction, transfers a skill from one body to another. This is the difference between automation and autonomy. Traditional automation follows a prepared path. Physical AI must choose a path. That choice requires perception, reasoning, and control. These three abilities are now becoming one stack. A camera produces images. A model interprets the scene. A planner decides what should happen. A control system converts the plan into movement. Sensors provide feedback. The machine adjusts. This loop happens constantly. See? Understand. Act, measure. Correct. A robot can repeat the loop thousands of times during one task. The better the loop becomes, the more of the physical world becomes addressable. This is why vision language action models have become so important. A language model connects words to concepts. A vision model connects images to concepts. A vision language action model connects words and images to movement. The user can say, "Put the green container beside the conveyor." The machine must identify the container, understand beside, find the conveyor, plan a safe route, choose a grip, move the object, avoid people, confirm the result. That sequence contains many problems once solved separately. Physical AI platforms want to solve them together. Google DeepMind's Gemini Robotics work represents one direction. The company describes models that allow robots of different shapes and sizes to perceive, reason, use tools, and interact with people. Its later Gemini Robotics EDU system was presented as a vision language action model that converts visual information and instructions into motor commands, with an emphasis on planning and learning across different robot bodies. The strategic idea is larger than one robot. Google wants intelligence that transfers. A skill learned on one embodiment can help another. A robotic arm learns something useful for a humanoid. A mobile robot learns navigation concepts useful elsewhere. The intelligence becomes portable, the model platform gains power over hardware companies, the robot body becomes an endpoint. The intelligence layer becomes the platform. This is the same abstraction battle seen in earlier computing eras. Hardware companies want the body to remain unique. Model companies want intelligence to move across bodies. The more portable the intelligence, the less control the manufacturer has over the software stack. NVIDIA is pursuing a broader infrastructure strategy. It wants to provide computing for training, simulation, development, and deployment. Its robotic stack includes Isaac tools, GR19 models for humanoid, Omniverse simulation, and Cosmos world models designed to generate and reason about physically grounded environments. The company is not betting on one robot brand. It wants every robot company to need NVIDIA somewhere. Train in the data center. Simulate in a virtual world. Run inference on the machine. Manage development through NVIDIAs. This is a familiar playbook. During the generative AI boom, NVIDIA did not need to own the most popular chatbot. It sold the scarce infrastructure used to build many of them. Physical AI gives the company another market for accelerated computing. Robots require training compute, simulation compute, synthetic data generation, edge inference. delete updates. NVID, I can sell across the entire life cycle. The company calls Physical A a next frontier because it expands demand beyond data centers into machines. This strategy is powerful for one reason. The final robot winners are uncertain. The infrastructure can win across many outcomes. Humanoids succeed. NVIDIA sells compute. Warehouse robots succeed. NVIDIA sells compute. Autonomous vehicles grow. NVIDIA sells compute. Industrial simulation expands. NVIDIA sells compute. This is the picks and shovels position in the most literal technology gold rush imaginable. But infrastructure dominance is never guaranteed. Customers do not want permanent dependence on one expensive platform. Robot companies may build custom chips. Cloud providers may offer alternatives. Open source models can reduce software lock-in. Edge devices have strict cost and energy requirements. The company that wins training does not automatically win deployment. Physical AI creates different computing markets. Massive data center training, high-performance simulation, low-power real-time inference, safety-critical control. Each can favor different architecture. NVIDIA wants the stack connected. Competitors want to separate it. This becomes a war over standards. Which model format? Which simulation environment? Which robot operating layer? Which sensor interfaces? Which skill representation? Which telemetry format? The technology that becomes standard can shape the whole market. Standards look boring. They are where platform power hides. Microsoft did not need to build every personal computer because Windows became the common layer. Google did not need to build every smartphone because Android became a common layer. A physical AI platform wants the same position. One software and development ecosystem across many machines. The problem is that the physical world is more fragmented than computing. A smartphone has a screen, processor, memory, battery, camera, and wireless connection. Robots have radically different bodies. A six-axis industrial arm. A warehouse cart. A drone. A quadrupes. A surgical device. A humanoid. A self-driving vehicle. The same intelligence cannot control them in exactly the same way. Embodiment matters. The shape of the machine determines what actions are possible. A model can understand the goal. It still needs to translate it all into movements appropriate for the body. This creates an opportunity for companies combining general intelligence with deep hardware knowledge. Boston Dynamics represents this engineering-first tradition. For years, its robots showed extraordinary movement. The challenge was turning research capability into scalable business value. The electric Atlas marks a more commercial phase. Boston Dynamics now presents Atlas as an enterprise humanoid for industrial material handling. In early the company said it was moving into production and scheduled deployments with Hyundai and Google. The partnership is strategically revealing. Boston Dynamics brings the body. Google DeepMind brings advanced AI models. Hyundai brings manufacturing, factories, capital, and a customer environment. This is what the physical AI looks like in practice. No single breakthrough. A coalition of capabilities. The body needs intelligence. The intelligence needs data. The data needs real deployment. Deployment needs manufacturing and service. Hyundai factories can become training grounds and customers. Google can test intelligence on a sophisticated platform. Boston Dynamics can accelerate from research to operation. Each side receives something difficult to build alone. Tesla takes the opposite approach. It wants to integrate most of the stack internally. Tesla already builds electric vehicles, batteries, power electronics, AI training infrastructure, cameras, autonomy software, and large manufacturing systems. Optimus extends those capabilities into humanoid robots. Tesla describes the goal as a general-purpose bipedal autonomous robot or boring tasks. The company says achieving this requires balance, navigation, perception, and interaction with the physical world. The strategic logic is clear. Tesla factories can provide initial tasks. Tesla's vehicle autonomy work can contribute perception and planning knowledge. That's manufacturing scale can reduce robot cost. Battery and motor experience can support the body. The company can become its own first customer. This is an enormous advantage if execution succeeds. Most robotic startups must find factories willing to tolerate early problems. Tesla owns factories. It can deploy internally, collect data, improve the robot, redesign the production line. The customer and vendor are the same company. Tesla also has a consumer brand and capital market access that few robotics companies can match. The company has said its next Optimus generation is intended for mass production, with production planned to begin before the end of RDO and eventual capacity ambitions far beyond today's humanoid market. These are company plans, not guaranteed outcomes. That distinction matters. Manufacturing a prototype is one achievement. Manufacturing thousands of reliable humanoids is another. Manufacturing at automotive scale is much harder. The supply chain must produce actuators, sensors, hands, computers, batteries, and structural parts with high yield. Every machine must survive long shifts. Service must be available. Safety must be proven. The robot must deliver useful work at a cost below alternative. Tesla is betting that vertical integration can solve these problems faster. If it succeeds, it can push prices down and force the entire industry to respond. If it fails, the same integration creates enormous complexity. Physical AI punishes weak links. A brilliant model cannot compensate. A low-cost body cannot compensate for poor task performance. A high-performing robot cannot compensate for weak service. The stack must work together. Figure is building another version of the integrated strategy. It combines humanoid hardware with Helix, its vision language action intelligence system. The company has emphasized moving from industrial deployments toward broad general-purpose capability. It also publicized operational experience with Figure R at BMW, including more than 1,000 hours of runtime and participation in production work, according to Figure's own reporting. The exact numbers matter less than the direction. Robot companies are moving from staged videos to measured operating hours. This is the metric shift that will determine the war. The market should care less about whether a robot can perform a surprising task once. It should care about whether the robot performs valuable tasks repeatedly. How many hours? How many interventions? What uptime? What cost? How much damage? How quickly does it learn a new workflow? The physical AI war will be won through operational data. Every hour in production teaches the system something simulation cannot fully provide. Unexpected object positions, lighting, dust, human behavior, tool wear, network failures, edge cases. The world creates the curriculum. The company with the largest useful fleet can learn faster. This creates a data flywheel. Deploy more machines, collect more experience, improve the model, increase reliability, win more customers, deploy more machines. This looks similar to autonomous vehicles. Tesla used fleet data as a strategic advantage in driving. Amazon uses real operations to improve warehouse automation. A physical AI company wants the same loop. Data becomes more valuable than the robot sale. The robot is the sensor network that collects it. This creates the second reason the physical AI war may produce giant platforms. Real-world data is difficult to copy. Internet text could be scraped by many companies. Physical interaction data is expensive. Someone must own the robot, place it in a facility, receive permission, operate it, record the sensors, label the outcome, protect customer information. The body is a data acquisition system. The company with deployment gains an asset competitors cannot download. This is why Amazon's position is stronger than it first appeared. Amazon said in RDO that it had deployed its 1 millionth robot across its operation. That fleet includes many forms, not humanoids, mobile drive units, robotic arms, sorting systems, inventory systems. The number demonstrates scale. Amazon also introduced a generative AI foundation model called Deep Fleet to improve movement coordination across its robotic network, saying it could improve fleet travel efficiency by 10%. 10% sounds modest. Across 1 million robots, 10% can be enormous. This is the economics of physical AI. Small improvements multiplied by giant fleets create large value. A model that makes one robot slightly better is useful. A model that makes 1 million robots slightly better is a platform. Amazon does not need to sell Deep Fleet as a public product for it to matter. It lowers costs and improves delivery inside the company's core business. This gives Amazon a different position in the war. NVID? It wants to sell infrastructure to everyone. Google wants transferable intelligence. Tesla wants vertically integrated products. Amazon wants operational advantage. The strongest physical AI system may remain internal because it improves another business. Warehouses become laboratories. Robots become infrastructure. The consumer never sees the platform. They receive a package faster. This is important because public attention can miss the largest deployment. The humanoid gets headlines. The logistics network produces cash flow. Amazon's robotics strategy also shows why specialized machines can be general robots. A warehouse task can be divided among systems optimized for movement, picking, storage, and sorting. The facility becomes the robot. One machine does not need to imitate a complete person. Software coordinates specialized bodies. This can be cheaper and more reliable. The physical AI war, therefore, has two competing visions: one general-purpose body learning many tasks, or a coordinated network of specialized machines. The future will contain both. The correct design depends on the environment. A fixed warehouse can be redesigned around specialized robots. An old factory may benefit from a humanoid that uses human tools. A home cannot contain a separate machine for every task. A general body becomes more attractive. The battle is not humanoid versus no humanoid. It is generality versus efficiency. Generality increases task range. Specialization lowers cost and improves reliability. The company must find a point where flexibility creates more value than complexity destroys. This is one of the deepest economic questions in robotics. A general robot may perform 10 tasks at 70% efficiency. 10 specialized machines perform each task at 99%. Which is cheaper? The answer depends on utilization. A specialized machine sitting idle is wasted capital. A general robot can move between jobs. If the general robot stays busy, lower task efficiency may still produce better economics. This is why companies compare productive hours. A robot that works 20 hours a day can justify high cost. A robot used 1 hour a day cannot. Generality is valuable when it raises utilization. It is marketing when it only raises expectation. The industry will learn this through deployment. The most successful robot companies may start with one narrow task and expand carefully. That strategy looks less revolutionary. It creates real data. The physical AI war will reward companies willing to be boring before becoming general. The next layer of the war is simulation. Real-world robot training is slow and dangerous. A machine cannot experience millions of failures inside a factory. It would break products, damage itself, interrupt work, possibly hurt people. Simulation creates experience without physical cost. A virtual robot can practice the same task thousands of times. Object positions can change. Friction can change. Lighting can change. The virtual environment can generate rare events. The system can learn recovery. This is why world models are becoming central. A world model attempts to represent how physical environments behave. If the robot pushes the object, what happens? If it grips too hard, does the object deform? If the floor is slippery, does the machine lose balance? If a person enters the path, what should happen? A sufficiently useful world model can become a training engine. NVIDIA's Cosmos strategy targets this layer. The company wants developers to generate and reason about physical scenarios at scale. The bigger ambition is not simply making realistic video. It is building a machine for producing physical experience. If synthetic data becomes good enough, companies can improve robots before hardware exists, test a new body virtually, train a skill, compare designs, find dangerous failures. then build. This reduces development cost. It also increases the power of the simulation platform. The physical AI company may depend on virtual worlds created by another company. The simulator influences what the robot learns. If the virtual physics is wrong, the real robot. This is called the simulation to reality gap. Closing the gap is a major competitive advantage. Companies use domain randomization. They change many virtual conditions so the model learns robust behavior. They combine synthetic and real data. They calibrate simulation against sensors. The better the pipeline, the faster the company can improve. Simulation becomes a factory for data. The chip company becomes a supplier of experience. This is why physical AI can drive enormous computing demand before robot sales become huge. Training millions of virtual episodes consumes infrastructure. One physical robot can have thousands of digital copies practicing in parallel. The virtual fleet can be larger than the real fleet. Every robot design creates simulation demand. This is the third reason the war reaches trillion-dollar scale. The market includes the compute used before the machine ever moved. The physical AI stack creates demand at every stage. Design, simulation, deployment, fleet operation, updates, analytics, security. The revenue is not one sale. It is a life cycle. This life cycle attracts cloud providers. Robots produce data continuously. Video, depth, force, position, temperature, failures, task outcomes. Some data is processed locally. Some is sent to the cloud. Models are retrained. Skills are distributed back to the fleet. The robot becomes an edge device connected to a global learning system. Cloud companies want this traffic. They can provide storage, training, device management, and marketplaces. A robot fleet can become a cloud workload measured in physical actions. This also creates a fight over where intelligence runs. Cloud intelligence offers powerful models and centralized learning. Edge intelligence offers low latency, privacy, and reliability. A robot cannot wait for the internet before avoiding a collision. Core safety must run locally. Complex planning can use larger remote models. The architecture becomes hybrid. The company controlling the handoff between edge and cloud can own another strategic layer. Which tasks run locally? Which data leaves the machine? Which model receives it? What happens when the network fails? These are technical and commercial decisions. A cloud provider wants more usage. A customer wants lower costs and stronger privacy. An edge chip company wants more local inference. The physical AI war is therefore also a war over data location. Homes and hospitals will push toward local processing. Warehouses and factories may use private networks. Consumer products may depend on cloud subscription. The balance will vary. Privacy can become a selling point. A home robot sees more than a phone. It sees rooms, objects, people, habits, children, health. A physical AI platform that mishandles this data can lose public trust quickly. Security is even more serious. I hack chatbot leaks word. The hacked robot can move. The machine may carry weight, operate near people, access secure areas, control doors, interact with vehicles. Cybercustodian becomes physical safe. This changes how platforms are evaluated. A model can not only be smart, it must be controllable. The robot needs identity, permission, signed software, secure updates, network isolation, logs, emergency stop, a way to fail safely. The control plane becomes part of the product. Every robot fleet needs to know which machine is this, who owns it, which software version is running, which skills are approved, what location is allowed, what task is assigned, who can take remote control, what happened before the incident. This is enterprise security for moving machines. The companies selling robot management can become another powerful layer. The physical AI war is not only about intelligence, it is about authority. Who is allowed to make the machine act? That question will shape regulation. A robot moving boxes inside a closed warehouse faces one standard. A delivery robot moving on a sidewalk faces another. A care robot assisting a patient faces another. An autonomous vehicle faces another. A humanoid inside a home faces another. The same foundation model may operate across all of them. The legal responsibility cannot be the same. The platform must understand context. This creates opportunities for safety systems, certification, audit, and insurance. Insurance may become a hidden force in the market. A customer wants to deploy robots. The insurer asks, what is the failure rate? What safety controls exist? Who maintains the machine? How is software updated? Can the robot be shut down remotely? What data proves performance? The answers influence premiums. A company with better fleet data receives cheaper insurance. Cheaper insurance lowers total cost. Lower cost wins customer. Safety data becomes an economic advantage. The robot company is not only selling capability, it is selling predictable risk. This is how a technology becomes infrastructure. The spectacular demo fades. The insurance underwriter becomes important. The physical AI market will mature when boring institutions can price it. Banks, leasing companies, auditors, regulators, maintenance networks. When these systems exist, deployment accelerates. The machine becomes financeable. This leads to another war. Who owns the robot fleet? The manufacturer can sell the robot. The customer can own it. A leasing company can finance it. A robotics as a service platform can retain ownership and charge per month or per task. Each model changes who captures value. Selling hardware creates revenue now. Service contracts create recurring revenue. Owning the fleet creates long-term cash flow and capital risk. The service model can transform adoption. A customer does not need to spend hundreds of thousands upfront. It pays for productive capacity, per hour, per pallet, per inspection, per item. The comparison moves from equipment price to labor cost. This makes the robot easier to buy. It also turns robotics into an asset. The vendor must manufacture machines before receiving years of payment. It needs capital, maintenance, insurance, residual value estimate. A robot subscription can look like software and behave like aircraft leasing. Investors must understand the difference. The service revenue is recurring. The asset is physical. It depreciates. It breaks. It requires field support. The margin depends on utilization and maintenance. A robot working most of the day can generate attractive returns. A machine sitting in a corner destroys capital. The platform that can keep fleets busy gains an advantage. This opens the possibility of robot labor networks. A customer requests physical work. The platform assigns available capacity. Robots move between jobs or facilities. Local service hubs maintain them. Skills are downloaded. The customer pays for the outcome. This is labor as an API. It is one of the largest possible business models in physical AI. Cloud computing allowed businesses to rent servers. Robot platforms may allow businesses to rent work. The company does not hire a worker or buy equipment. It calls physical capacity through software. This model will begin in structured environments, warehouses, factories, construction projects, agricultural season, hotel cleaning. The network effect can be powerful. More robots create better coverage. Better coverage attracts customers. More customers increase utilization. Higher utilization lowers cost. Lower cost attracts more demand. The platform collects data from every task. The data improves the fleet. This is a marketplace and learning flywheel at the same time. The physical limitation is location. Compute can move across a network instantly. Robots cannot teleport. The platform needs depots, transportation, technicians, and local inventory. This makes physical AI more operationally difficult than cloud computing. It also protects companies that master real-world logistics. The winning platform may combine global software with local service. This is not a pure software business. It is a technology-enabled industrial network. That distinction will decide valuations. A market may reward the company like a platform during growth. Cash flow will reveal whether it is a platform or a capital-heavy service operator. The strongest companies can become both. Gay utilization, standard hardware, automated maintenance, low intervention, reusable skills, data advantages. This can push margins upward over time. The physical war is a race down the cost curve. Every layer must become cheaper. Computing, sensors, actuators, batteries, manufacturing, intervention, service, the company that lowers total cost per useful hour fastest wins. This is more important than robot price. A cheap robot needing constant human help is expensive. An expensive robot operating reliably for years can be cheap. Customers will calculate full cost, purchase or lease, installation, integration, energy, maintenance, downtime, supervision, floor space, insurance. The robot must beat the alternative. The alternative may be human labor. It may be a conveyor, a traditional industrial arm, a process redesign, outsourcing, doing nothing. Ethical AI competes with all of them. The industry can overestimate the market by comparing robots only with wages. Human workers bring flexibility, judgment, communication, and informal knowledge. A robot may automate one task while the employee performs 10 others. The customer cannot remove the entire role. The true savings are smaller. This is why task analysis matters. The physical AI company should target workflows where the robot captures a large share of useful activity. A narrow but complete task is better than a broad partial task. Move every container from one point to another. Inspect every gauge. Load every machine. Sort every packet. These are clear units of value. The robot economy begins with complete workflow. Generality expands later. This is also why industrial customers are the first battleground. They measure work precisely. A factory knows cycle time. A warehouse knows throughput. A logistics network knows package cost. The company can prove return. Homes are harder. The value of tidying a room is subjective. Safety expectations are higher. Utilization may be low. A consumer humanoid is the largest dream and the slowest business. Industrial physical AI can become enormous before the home market arrives. This matters for the trillion-dollar thesis. A market does not depend on one robot in every house. Global manufacturing, logistics, construction, agriculture, transportation, energy, and healthcare are already enough. A small percentage of these activities creates a huge market. The war can be massive without total labor replacement. That is the rational version of the story. The irrational version says robots will do everything immediately. That creates hype. Hype attracts capital. Capital accelerates research. It also creates bubbles. The physical AI will produce both real transformation and spectacular failure. Many robot startups will run out of money. Hardware development is slow. Manufacturing is expensive. Customers take time. Pilots do not always become orders. Large announcements may be non-binding. A company can show an impressive robot and still fail to produce at scale. Investors must separate the layers of proof. A prototype proves possibility. A pilot proves customer interest. A deployment proves operation. A renewal proves value. Positive unit economics prove a business. Mass manufacturing proves scale. Each stage is different. A market often prices stage 1 like stage 6. This creates volatility. The strongest companies will release operational evidence. Hours worked, intervention rate, uptime, safety incidents, tasks completed, customer expansion, cost per hour, manufacturing yield. These numbers are harder to fake than a video. The physical AI war will gradually become a metrics war. This is healthy. The industry needs credibility. The company with honest performance data can build trust with customers, insurers, regulators. and financiers. Trust lowers friction. Lower friction accelerates deployment. The platform war is not only technical, it is institutional. The next decisive battlefield is the body. Artificial intelligence can improve quickly through software updates. A robot cannot download a better gearbox. It cannot patch a weak joint. It cannot use a new hand if the mechanical system was never designed for it. Physical AI is limited by physical engineering. This is where the trillion-dollar story becomes an industrial story. A robot body is a supply chain. Motors, reducers, bearings, encoders, force sensors, cameras, wiring, control boards, batteries, cooling systems, frames, protective covers, hands, feet. Each component affects cost, weight, speed, precision, energy use, and reliability. A failure in a cheap connector can stop a robot with hundreds of thousands of dollars. A small amount of mechanical play can ruin manipulation accuracy. Heat can reduce performance. Dust can damage sensors. Repeated movement can break cables. The physical world finds weaknesses software testing misses. This creates enormous opportunity for component suppliers. The public sees the robot brand. Industrial value can flow to the company producing the best actuator at scale. An actuator combines movement and control inside a joint. Humanoid robots may need dozens of them. They must be powerful enough to lift, light enough to carry, efficient enough to preserve battery, precise enough for delicate work, cheap enough for mass production, reliable enough for years of repetitive movement. Improving all of these at the same time is difficult. The actuator market can become one of the hidden centers of the war. The same is true for precision reducers. Motors spin quickly. Robot joints often need slower, controlled height work movement. Reduction systems translate motor speed into useful force. High-quality components are expensive and hard to manufacture consistently. A robot company promising massive production needs a massive supply chain behind the promise. This is where China's position becomes strategically important. China has a deep ecosystem for electronics, batteries, motors, machinery, industrial components, and large-scale manufacturing. It is also the largest market for industrial robot installation. Domestic factories create demand. Suppliers create cost advantages. Government policy supports advanced manufacturing. Competition among local robot companies pushes prices downward. This combination can compress the cost curve faster than many Western startups expect. A Chinese company does not need to invent every component from zero. It can access a dense industrial network. Prototype, source parts, redesign, manufacture, scale. The feedback loop is faster when suppliers are nearby. This is the same advantage that helped China dominate parts of solar, battery, drone, and electric vehicle manufacturing. Physical AI can follow a similar pattern. The United States remains powerful in foundation models, advanced chips, software, venture capital, cloud infrastructure, and major technology platforms. China is powerful in manufacturing depth, component cost, supply chain speed, and deployment scale. The war is not simply one country against another. It is a competition between different strengths. The winning ecosystem may combine American intelligence with Asian manufacturing. Or geopolitical tension may force more separation. Export controls can limit chips. National security rules can restrict robot software. Governments can demand local data. Companies can be excluded from critical infrastructure. Physical AI sits at the intersection of economic and military capability. A robot that moves boxes can share technology with a robot operating in dangerous environments. Autonomous navigation can support civilian and defense applications. Drones already demonstrate how quickly commercial systems can become strategic. Governments will not treat physical AI like an ordinary consumer app. This can split the global market. Different standards, different chips, different software ecosystems, different data rules, different supply chains. Fragmentation raises cost. It also creates protected regional champions. A company dominant in one country may struggle to enter another. This gives local industrial groups an advantage. Japan has decades of robotics expertise. South Korea has high automation density, electronic and manufacturing strength. Germany has industrial engineering and factory customers. Europe has safety regulation and advanced machinery. The United States has AI platforms and capital. China has manufacturing scale and domestic demand. No region owns every layer. This creates a global chessboard. Partnerships matter. So do acquisitions. A software company can buy a robotic steam. An automaker can invest in a humanoid platform. A component supplier can move upward into complete system. A robot startup can partner with an industrial service network. The market will consolidate because the stack is expensive. Building intelligence, body, manufacturing, sales, service, and financing independently is almost impossible for a young company. Some startups will remain specialized. A hand company, a tactile sensor company, a simulation company, a robot data company, a safety company. Specialization can be a strength. The component becomes standard across many robot brands. The supplier earns regardless of which body wins. This is why the next giant may have a name the general public does not know. The world's most valuable physical AI business could sell a component hidden inside millions of machines. The same pattern happened in semiconductors. Consumers knew computer brands. Investors learned to understand chip architecture. Physical AI will teach the market to understand actuators, torque density, tactile sensing, battery cycles, and intervention rates. Robot hands deserve special attention. Walking looks dramatic. Hands create economic value. A robot can move through a factory. Without reliable manipulation, it cannot perform most human tasks. The human hand is an extraordinary machine. Many joints. Sensitive touch. Fine force control. Ability to grip a heavy tool and a fragile object. People adjust constantly without thinking. A bottle slips. The fingers increase pressure. A cable catches. The hand changes angle. A soft object deforms. The grip adapts. Robot hands struggle because vision alone is not enough. The machine needs touch, force, texture, slip detection, position. The hand must survive impacts and remain affordable. Complex hands can become fragile. Simple grippers can be reliable but limited. The industry is searching for the right balance. A five-finger hand looks human. A two-finger gripper may complete the task more cheaply. Again, the market rewards useful work. The hand company solving robust manipulation can unlock many jobs at once. Machine tending, order picking, assembling, food handling, laundry, tool use. This layer can become as important as the robot brain. A powerful model trapped in an unreliable body creates no economic value. This is one reason hardware-software co-design matters. The model should understand the body's limits. The body should expose useful sensor data. A grip planner designed for one hand does not transfer perfectly to another. The companies integrating the layers may achieve better performance. The companies building open standards may achieve broader adoption. The war between integration, openness repeats. Tesla wants deep integration. In VID, I wants a broad ecosystem. Google wants intelligence across embodiment. Industrial incumbents want compatibility with existing systems. Startups want freedom to differentiate. Customers want choice and reliability. No one receives everything. The market will find several dominant architectures. Another battlefield is the robot operating system. A physical machine needs low-level control, communication between sensors and motors, safety, device drivers, navigation, planning, logging, application interfaces. Developers need a common environment. ROS, the robot operating system ecosystem, has played a major role in research and development. Commercial platforms build on or beyond it. The next stage is an enterprise-grade operating layer for fleets. Secure updates, identity, permission, skill deployment, hardware abstraction, real-time monitoring, simulation links. The operating system can become the bridge between intelligence and body. Own the bridge and you influence both. A robot manufacturer can keep the operating layer proprietary. This creates control and consistency. It can also slow third-party development. An open system attracts more developers. It can create fragmentation and security risk. The smartphone market solved this with controlled platforms and app store. Physical A may develop skill store. A warehouse buys a pallet handling skill. A factory buys a machines loading skill. A hotel buys a cleaning skill. A hospital buys a supply delivery skill. The skill is tested for certain robot bodies and environments. The customer installs it. The machine gains a new job. This is the software dream inside robotics. Hardware becomes more valuable over time. Developers can participate without building a complete robot. A marketplace can take a fee. The platform owner controls distribution. The economic potential is enormous. The safety challenge is much greater than a phone app. A bad game crashes. A bad robot skill can damage equipment or injure someone. Every skill needs verification. Which hardware is compatible? What weight can it handle? What sensor quality is required? What environments were tested? What happens when confidence is low? Who is liable? The skill marketplace may resemble an app store combined with industrial certification. This favors platform companies with testing infrastructure. Simulation can test thousands of scenarios. Real facilities still require validation. Insurance can require certification. The platform can collect performance data from deployed skills. High-performing skills rank higher. Developers receive revenue based on usage. This creates another data flywheel. The robot operating platform can become the most powerful layer of the economy. It knows which skills are used, which robot brands perform best, which customers need more capacity, which tasks remain unsolved. The platform can build competing first-party skills. Developers fear the gatekeeper. The same conflicts from mobile return, commission rates, self-P referencing, access to customer data, approval delays, platform lock-in. The difference is that industrial customers have more negotiating power than consumers. Large manufacturers can demand open interfaces. They can fund independent standards. They can build custom skills. A market may remain more open and smart. Small businesses may depend on turnkey platforms. The vendor can bundle body, skills, financing, service, and insurance into one package. Convenience creates lock-in. This is the full-stack robot offer. The customer does not want a robotics project. It wants the task completed. The vendor says, "We will install the machine, train the skill, maintain it, operate remote support, guarantee uptime, charge per month." The customer buys an outcome. This moves competition away from technical specification. The vendor with the most complete service wins. Physical AI becomes service as software in the most literal form. A digital platform sells physical results. This can change traditional outsourcing. Today, a company hires a contractor for cleaning, security, logistics, or maintenance. Tomorrow, the contractor may operate a mixed human and robot workforce. The customer pays the service company. The service company decides how much work is automated. This is a likely route to adoption. The customer does not need to become a robotics expert. Existing service providers become distribution channels. A cleaning company deploys cleaning robots. A logistics company operates warehouse robots. An equipment rental company rents autonomous machines. A hospital services company manages delivery robots. This can be faster than robot startups selling directly to every business. Distribution is one of the hidden war. Who already has the customer? Who understands the workflow? Who can provide local support? Who can finance equipment? A technically superior robot with no distribution can lose to an adequate robot bundled through a trusted network. This is why industrial giants remain dangerous competitors. They have decades of customer relationships. A factory manager may trust an established automation vendor more than a startup. The startup must prove support. The incumbent must prove intelligence. Partnerships solve the gap. The physical AI market will be filled with alliances because no company begins with everything. The largest early market remains logistics. Movement is measurable. Warehouses are structured. Labor is repetitive. E-commerce creates demand. Amazon's million robots shows how much automation can exist without humanoids. Other logistics companies, retailers, and warehouse operators want similar productivity. They may not have Amazon's internal engineering resources. This creates a market for external platforms. Autonomous mobile robots already move inventory. Robotic arms pick and sort. AI systems coordinate routes. New physical AI and models can improve perception and adaptability. The next battle is unstructured picking. Boxes are easier than clothing. Rigid objects are easier than soft bags. Known inventory is easier than random returns. Every improvement opens more of the work. Warehouse economics can support specialized systems. The facility can be redesigned. This makes logistics a proving ground, not necessarily the final form. Manufacturing is the next major battlefield. Factories contain high-value repetitive tasks and severe reliability requirements. A robot that slows the line is unacceptable. A robot that fills a labor shortage can be extremely valuable. Automotive companies are early partners because they understand automation and operate large factories. Figure worked with BMW. Boston Dynamics is working with Hyundai. Tesla can deploy inside its own facilities. These are not random partnerships. Automotive manufacturing offers structured tasks, engineering support, and high labor intensity. It also provides brutal validation. If a humanoid works reliably on a production line, credibility rises. The first jobs will likely be material movement and machine loading rather than complex assembly. Carry parts, place containers, move components between stations, handle repetitive lifting. The robot learns the rhythm of production. Later, it can add manipulation. Inspection. Tool use. The market expands from mobility to dexterity. This gradual expansion matters. Investors imagine a general factory worker. Customers buy one completed test. Healthcare can create a large but slower market. Physical AI can transport supplies, clean rooms, assist laboratories, support rehabilitation, and help move patients. Direct clinical care requires higher trust. A robot can fetch equipment before it gives medical advice. The infrastructure tasks are large enough to build a business. Hospitals have labor shortages and expensive work. They also have strict privacy, safety, and procurement requirements. A vendor succeeding in healthcare gains credibility. The sales cycle is long. The customer relationship can be durable. The robot platform must integrate with elevators, doors, inventory, and hospital systems. Again, workflow integration creates the moat. Agriculture creates a different war. The environment is unstructured. Weather changes. Plants vary. The ground is uneven. The machine must be rugged. Specialized robots can identify weeds, apply chemicals precisely, monitor crops, and assist harvesting. The value includes lower input use and higher yield. Not only labor savings, a vision model that identifies each plant can change farming economics. Digital AI can make precision agriculture affordable. The market is global and fragmented. Farm size varies. Crop types vary. Local service matters. The winning company may specialize by crop and region. General intelligence helps. Physical adaptation remains local. Construction is even more variable. Every site changes. The industry has low productivity growth and serious safety risk. Robots can handle layout drilling, material movement inspection, and specific repetitive construction tasks. Autonomous heavy equipment may create more value sooner than humanoid. The machines already exist. Add perception and autonomy. A loader can move material. An excavator can follow a plan. A drone can inspect progress. Physical AI upgrades industrial equipment into robotic equipment. This is a huge market often ignored by humanoid coverage. The next trillion-dollar war may be won partly by companies making ordinary machines autonomous. Tractors, forklifts, mining trucks, cranes, excavators, cleaning machines, industrial vehicles. They already have bodies. They need intelligence. This is faster than inventing new hardware from zero. Legacy equipment manufacturers have an advantage. They know the machine, customers, and maintenance network. AI companies can partner. The war expands across the entire industrial economy. Autonomous driving is physical AI at massive scale. Vehicles perceive, plan, and act in the real world. The research, chips, sensors, simulation, regulation, and fleet systems overlap with robotics. Tesla's Optimus and vehicle autonomy as related programs. NVIDIA provides automotive and robotics platforms. Google's history with autonomous driving contributes to physical world intelligence. The boundary between robot and vehicle is artificial. A vehicle is a robot with a transport function. A drone is a flying robot. A warehouse cart is a logistics robot. The physical AI market becomes much larger when viewed this way. Humanoids are the symbol. Autonomous machines are the economy. The same foundation technologies can spread across bodies. This creates economies of scope. A company developing perception for vehicles can reuse parts in robots. Simulation environments can train both. Edge chips serve both. Mapping and localization transfer. This is another reason major technology companies enter physical AI. They can reuse existing investment. The consumer home remains the largest long-term prize. A useful home robot can become a new computing platform. The smartphone owns attention. The home robot can own action. It can move through private space, handle objects, monitor condition, connect digital services to physical tasks. The company controlling it gains a deep customer relationship. This is why home robotics attracts huge ambition. The technical and social barriers are higher than industrial deployment. Homes are chaotic. People expect near-perfect safety. Price must fall dramatically. Privacy must be exceptional. Service must reach millions of individual customers. The robot must perform enough useful work to justify purchase or subscription. A device that folds one shirt impressively may not have a business. A device providing hours of daily assistance can. Elder care may become an early driver. Aging societies need support. Robots can assist with carrying, reminders, monitoring, communication, and simple household tasks. They do not replace human care. They can extend independence and reduce physical strain. The ethical questions are serious. Who sees the camera? How is health information used? Can family members monitor the user? Does the robot create companionship or substitute for human contact? The company entering the home becomes responsible for more than engineering. Trust becomes the product. This may favor brands with strong consumer relationships. It can also create room for new companies built around privacy. On-device intelligence becomes strategically important. A home robot should not send every conversation and image to a remote server. Edge compute protects privacy and reduces latency. Cloud systems provide stronger models. The product must balance them. This is another layer of competition. Who builds the efficient local model? Who builds the edge chip? Who controls updates? Who controls memory? The home robot may become the ultimate personal AI assistant because it can act. A digital assistant knows the schedule. A physical assistant can prepare the environment. This merges to giant platform war. Personal AI and physical AI. The company controlling both can know what the user wants and execute it in the world. That position would be extraordinarily powerful. It also creates extreme concentration of private data. Regulation will follow. The physical AI war will not be decided only by companies. Governments will choose winners through procurement, standards, subsidies, safety rules, and trade policy. Industrial automation affects national competitiveness. Countries with aging populations need productivity. Countries seeking manufacturing independence need robots. Defense agencies need autonomous systems. Infrastructure projects need machines. Public money will flow. This can accelerate domestic industries. It can also create politically protected markets. A company aligned with national strategy gains capital and customers. A foreign platform may face restrictions. Physical A, I can become as strategic as semiconductors. The two are connected. Advanced robots need chips. Chip controls can limit robot capability. Robot supply chains can become part of economic security. The United States and allies may try to protect high-end computing. China may accelerate domestic alternatives. Europe may push for safety and sovereignty. The global stack can split. Companies will need multiple versions, different chips, different clouds, different data centers, different compliance. This raises cost but creates demand for regional integration. The war becomes a marathon. The trillion-dollar estimate should be understood as a strategic possibility, not a guaranteed annual market tomorrow. Physical A, I can capture value from many existing markets. Industrial automation, vehicles, logistics, machinery, cloud computing, labor services, semiconductors, software, insurance, finance. The total opportunity becomes enormous because categories overlap. Counting all of them can exaggerate markets' eyes. The better question is where new profit pools appear. Robot intelligence platforms, simulation, synthetic data, autonomous machine upgrade, fleet software, robot skills, RAS financing, safety certification, remote operations. These are genuinely new or rapidly expanding layers. The companies capturing them can become very large. The market will not distribute value evenly. Some hardware becomes commoditized. Some software becomes open source. Some services remain low margin. The scarce layer captures profit. Today, advanced chips and high-quality robotics talent are scarce. Tomorrow, reliable manipulation data may be scarce. Later, customer distribution and maintenance may be scarce. The center of value moves as the industry matures. Smart investors track scarcity. Smart companies try to own the next bottleneck before the current one disappears. NVIDIA owns a powerful computing bottleneck. Google aims for general intelligence. Tesla aims for manufacturing and fleet integration. Amazon owns deployment and workflow data. Boston Dynamics owns advanced embodiment knowledge. Chinese ecosystems can own cost and supply chain scale. Industrial companies own distribution and service. No one has won. The war is open because the stack is unfinished. This is the moment when platform positions are created. Once a standard becomes deeply embedded, displacement is difficult. A factory choosing one robot ecosystem trains employees, integrates systems, buys skills, and builds data around it. Switching becomes expensive. Early deployments can create decades of customer lock-in. This raises the stakes of today's pilot. A pilot is not only revenue. It is a chance to become the standard inside a facility. The vendor learns the workflow. The customer becomes dependent on the vendor's data and skill. The first supplier can expand across the site. This is land and expand strategy in physical form. Enterprise software used it. Robotics can use it with stronger switching costs. The machine is bolted into operation. The vendor becomes part of production. This is why customer access matters so much. Automotive factories, Amazon warehouses, Hyundai facilities, BMW plants. These are not only places to test robots. They are strategic beachheads. The company proving value in one plant can move to others. The physical AI war is fought facility by facility before it is won globally. The labor question will decide whether physical AI receives public support or public resistance. Companies usually introduce robots through the language of safety, productivity, and labor shortages. These reasons can be genuine. Many physical jobs are dangerous. Repetitive lifting damages bodies. Night shifts are difficult to staff. Aging societies face growing care needs and smaller working age population. Robots can reduce injury and fill gaps. They can also replace existing workers, weaken wage bargaining, increase monitoring, and intensify the pace of work. Both stories can exist at the same time. The outcome depends on deployment. A warehouse robot can carry heavy loads so employees avoid strain. The same system can measure every human movement and raise performance targets. A factory robot can remove dangerous work. The company can share productivity gains through wages and shorter hours, or it can cut staff and push remaining workers to supervise more machines. Physical AI does not decide the distribution. Ownership and management decide. This is why the phrase robots will create new jobs is not a complete answer. New jobs will appear. Robot technicians, fleet operators, safety engineers, simulation designers, data specialists, integration experts, field service, remote intervention, insurance, auditing. The person losing one job may not automatically receive the new one. The new role may require different training, exist in another city, pay differently, arrive years later. Economic transitions can create growth and pain at the same time. The physical AI war will therefore include a political war over who receives the gains. The owner of robot capital earns returns. A worker earns wages. As more production moves from wages to machine ownership, income can shift toward capital. This can increase inequality even while total output rises. The robot economy may produce cheaper goods. People still need income to buy them. If automation advances faster than income systems adapt, demand becomes a problem. This is not a technical issue. It is a macroeconomic issue. Governments will debate training funds, labor protections, taxation, reduced working hours, employee ownership, and social support. The debates will become louder as machines move from factories into visible public and service roles. A software system replacing part of office work can be invisible. A humanoid entering a workplace is a symbol. Workers can point to it. Media can film it. Political reaction can accelerate. Robot companies need social strategy, not only engineering. They should involve workers in deployment. Explain which tasks change. Provide training. Design safe interaction. Measure injuries and stress. Give humans authority to stop machines. A company treating employees as obstacles can create resistance and hidden failure. Flatline workers understand the workflow better than a remote robotics team. They know where objects get stuck, which parts arrive damaged, which shortcut keeps the process running, which exception happens every Friday. Their knowledge can make the robot successful. The physical AI company needs them. If workers believe they are training their replacements without benefit, cooperation falls. Responsible adoption can become a competitive advantage. Customers want projects that survive politically and operationally. A robot vendor promising quick headcount cuts may win attention. A vendor showing safer work, higher throughput, and a credible transition may build durable relationships. The war will produce different business cultures. One views humans as temporary obstacles on the path to full automation. Another views machines as tools inside human systems. The second may move slower. It can face less backlash and learn more from operations. The first may capture larger upside if full autonomy arrives quickly. It carries greater execution and social risk. No one knows which approach wins in every market. The safest prediction is that mixed systems dominate for a long time. Humans and robots working together. Software agents coordinating tasks. Remote operators handling uncertainty. Technicians maintaining fleets. The share of machine work increases gradually. The facility becomes more autonomous without becoming empty. This mixed reality creates the largest near-term market. A robot does not need to replace a complete employee to create value. It can remove one physically difficult task. Allow one worker to supervise several stations. Extend operation into the night. Reduce downtime. Improve quality. The productivity gain accumulates. This is less dramatic than replacement. It is how industrial transformation usually happens. Physical AI spreads through workflow redesign. The company changes the process around the machine. A factory removes unnecessary movement. A warehouse rearranges storage. A hospital changes supply routes. A robot becomes a reason to modernize operations. Some value comes from the machine. Some comes from process reform. Consultants and integrators capture this opportunity. The physical AI war creates a huge services market because every environment is different. Mapping, safety assessment, data preparation, workflow design, installation, calibration, employee training, system integration. A robot platform claiming zero integration may succeed in simple tasks. Complex facilities require expertise. The services layer can slow margins and accelerate adoption. Large consultants will build physical AI practices. Industrial distributors will become integrators. Equipment dealers will adopt autonomous systems. The ecosystem expands around the technology. The trillion-dollar battle is not only a battle among famous AI companies. It includes thousands of regional businesses making deployment possible. The local technician may be as important to uptime as the global foundation model. This is the physical difference. Software can be distributed instantly. A broken joint needs someone nearby. The company winning globally needs local capability. Service centers, spare parts, customer support. A robot platform without a service network is incomplete. Boston Dynamics has highlighted field application engineering and regional support as it expands. Industrial incumbents already possess this muscle. Tesla has service and manufacturing experience but faces a new class of machine. Amazon can maintain its own fleet inside controlled operation. Startups must build or partner. The service war will be less visible than the model war. It can decide commercial success. The same is true for manufacturing yield. A company can design one excellent robot. Mass production requires every unit to meet quality standards. Component variation affects movement. Calibration consumes time. A small defect causes field failure. Production lines need tests. Suppliers need consistency. The robot company becomes a manufacturing company whether it wants to or not. Software culture celebrates rapid iteration. Industrial customers dislike constant hardware changes. They need stable parts and long support. The physical AI winner must combine fast software improvement with slow, disciplined hardware lifecycle management. This cultural combination is rare. Move fast in simulation. Move carefully in factories. Update intelligence often. Change safety-critical hardware deliberately. The organization needs to speed. Companies built only around research can struggle with product discipline. Industrial incumbents can struggle with AI speed. The winner builds both cultures or creates partnerships. This is why the market remains open. No company has a perfect starting position. NVIDIA has computing and ecosystem strength, but it does not own the final customer in every industry. Google has advanced models, but it must convert research into physical deployment. Tesla has integration and manufacturing ambition, but humanoid scale remains a difficult execution challenge. Amazon has unmatched internal fleet experience, but much of the value remains tied to its own network. Boston Dynamics has deep robotics engineering, but it is moving from limited deployments toward product scale. Figure has speed and capital, but it must prove reliability and economics across larger fleets. Chinese manufacturers can drive costs down, but international access and high-end computing can become constraints. Industrial giants have customers, but software platforms can move faster. The war will not end with one universal winner. Different companies can dominate different layers. One chip platform, several foundation models, multiple robot bodies, regional manufacturing leader, industry-specific integrators, a few fleet and skill platforms. The economic power depends on where switching costs become highest. The model can be replaced if interfaces are open. The robot body can be replaced if skills transfer. The fleet platform can be replaced if data is portable. The customer workflow is hardest to replace. The company integrated deepest into operations may capture the strongest moat. This is why physical AI startups should not sell only technology. They should solve the complete work. The workflow creates data, trust, and renewal. A customer does not renew because the robot is advanced. It renews because production improves. The most important word in physical AI is not artificial. It is physical. Physical systems obey constraints, gravity, Action, where, energy, distance, time. These constraints create slower progress than software hype suggests. They also create more durable value once solved. A competitor can copy an app feature quickly. They cannot instantly copy a manufacturing line, service network, fleet history, and field reliability. Physical moats are expensive. They are real. This can make the final winners extraordinarily valuable. The market may eventually resemble a combination of semiconductors, cloud computing, industrial automation, and automobiles. Each of those industries supports enormous companies. Physical AI combines their demand. Chips provide intelligence. Cloud and simulation provide training. Industrial systems provide deployment. Vehicle-style manufacturing provides scale. Software provides recurring revenue. Finance provides fleet expansion. This is the trillion-dollar argument. Not one company earning $1 trillion from humanoids. A new technology stack influencing trillions of dollars of labor, machinery, and production. The value is distributed. The platform controlling the highest leverage layer can capture a large share. The exact winner depends on how the stack evolves. Scenario 1 is the NDID outcome. Physical AI remains fragmented across many robot makers. They all need a common computing, simulation, and development platform. NVID, IA becomes the infrastructure standard. Hardware brands compete above it. The platform captures profit across the market. Scenario 2 is the Tesla outcome. Vertical integration wins. Tesla achieves low-cost mass production, collects fleet data, and distributes a general humanoid platform. Its factories provide early scale. The robot becomes another Tesla product and service network. The company owns body, intelligence, manufacturing, and customer relationship. Scenario 3 is the Google outcome. General robot intelligence becomes portable across bodies. Model quality matters more than hardware brand. Google DeepMind licenses or distributes the intelligence layer broadly. Robots become endpoints for Gemini-class physical models. Scenario 4 is the Amazon outcome. The largest value remains internal. Companies with massive operations build proprietary robot fleets that improve logistics, manufacturing, and delivery. Physical AI becomes an operational moat rather than a standalone product market. Scenario 5 is the China scale outcome. Cost falls faster than expected. Chinese manufacturers produce large volumes of capable robots and components. Hardware becomes affordable and widely available. Software ecosystems grow around the installed base. Western companies retain model and chip advantages but lose part of manufacturing value. Scenario 6 is the industrial incumbent outcome. Customers prefer proven automation suppliers with service networks, safety expertise, and integration capability. AI startups become technology providers or acquisition targets. The old industrial giants absorb physical AI. The actual future can combine all six. NVID, IA supplies compute. Google supplies models. Chinese factories produce components. Industrial companies integrate. Amazon operates fleets. Tesla competes vertically. The market can support multiple trillion-dollar value chains. This is what makes the war so broad. The critical uncertainty is how much intelligence becomes commoditized. The foundation models for robotics become widely available. Hardware data and deployment gain value. If a small number of models remain far better, model providers gain power. If bodies become standardized, software gains. If hardware differences remain critical, manufacturers retain control. If simulation closes most of the data gap, platforms with compute win. If real-world data remains essential, deployed fleets win. If general humanoids achieve strong economics, the market consolidates around flexible platforms. If specialized robots remain cheaper, the market stays fragmented by task. Every investment thesis is a bet on these uncertainties. The physical AI war can create winners at every stage. Early stage: chips, simulation, research tools, sensors, and components. Middle stage: industrial deployment, remote operation, and integration. Later stage: skill marketplaces, robot labor networks, consumer robots, and autonomous organizations. The timing differs. A company can be right about the destination and fail because it arrives too early. Capital intensity makes timing dangerous. A robot startup spends money before the market is ready. A component factory builds capacity before orders materialize. A fleet operator finances machines with low utilization. The technology improves. The company still runs out of cash. This happened in previous technology booms. The dot-com era produced the internet and many bankruptcies. Clean technology created enormous industries and painful cycles. Electric vehicles transformed markets while many companies failed. Physical AI can follow the same pattern. The category can explode. Individual investments can implode. The distinction is essential. The title describes a technology war, not a guarantee that every participant becomes valuable. The market will reward operational evidence. Factories using the system, customers expanding orders, lower intervention, falling cost, improving gross margin, reliable manufacturing, service efficiency. A company without these signs may be selling a story. Stories attract early capital. Economics attracts lasting capital. The public companies and startups involved will make enormous forecasts. Some will be sincere ambition. Some will be fundraising. The investor should ask, what task is completed today? In what environment? How often? With how much human health? At what total cost? How many units are operating? How many customers expanded after the pilot? What fails most often? Who repairs it? These questions cut through spectacle. A robot can dance and still be a bad business. A machine moving boxes quietly can create billions in value. The physical AI war will look less cinematic as it succeeds. The technology disappears into operation. A warehouse does not advertise every algorithm. The customer notices faster delivery. A factory does not celebrate every robot step. It notices output and safety. The final winners become infrastructure. Infrastructure is used more than admired. This is the destination every platform become necessary. The company cannot operate without your chips, your model, your fleet software, your service network, your skills, your data. This necessity creates pricing power. It also creates regulatory attention. A physical AI platform influencing factories, transport, and labor can become systemically important. Governments may require interoperability, cybersecurity standard, local control, emergency access, data rules, competition policy. The more successful the platform becomes, the more political it becomes. The same occurred with cloud and mobile platforms. Physical AI affects national production directly. Regulators may act earlier. The industry can reduce backlash by supporting open standards, allowing data export, providing transparent safety evidence, avoiding deceptive autonomy claims, protecting worker and customer privacy, making machines repairable. These choices can slow short-term lock-in and support long-term adoption. Trust is an economic asset. One major accident, security breach, or privacy scandal can damage the entire market. Companies share responsibility for category credibility. The war encourages speed. Safety requires patience. This tension cannot be eliminated. The best companies create systems where speed and safety reinforce each other. Simulation finds failures before deployment. Fleet monitoring catches unusual behavior. Remote assistance prevents dangerous action. Software updates improve every machine. Standard components reduce field problems. Better control increases customer confidence. Confidence increases deployment. Safety becomes a growth engine. Physical AI also has an environmental dimension. Robots can improve precision, reduce waste, optimize energy, use fewer chemicals, maintain equipment before failure. They also require metal, batteries, chips, and electricity. Mass deployment creates material demand. The environmental outcome depends on design and use. A robot increasing warehouse throughput can enable more consumption. An agricultural robot reducing herbicide can create direct benefit. A repair robot extending infrastructure life can save resources. A mining robot can make extraction easier. Technology has no single environmental direction. Policy and economics shape it. Energy efficiency will become a competitive metric. A robot working longer on the same battery produces more value. Efficient actuators, lightweight structures, better motion planning, low-power chips, energy-aware fleet scheduling. These improvements lower cost and environmental impact at the same time. The battery industry becomes part of the war. Robot demand may be smaller than vehicle demand initially, but performance requirements differ. High cycle life, safe operation indoor, fast charging, swappable packs, compact form. Battery suppliers can create specialized products. Charging infrastructure enters facilities. Robot fleets become another electrical load. Energy management software schedules charging. The physical AI ecosystem touches utilities. Telecommunications also matter. Robots require reliable connectivity. Factories can use private networks. Warehouses need coverage. Remote operation requires low latency. Cloud updates require bandwidth. Connectivity failures require local autonomy. Telecom providers can sell robot-ready networks. The technology war spreads into industries far from AI research. Real estate becomes robot-ready. Buildings include charging stations, automatic doors, maps, maintenance zones, and robot routes. Construction companies design for machines. Insurance changes premiums based on automation. Education trains technicians. Finance creates robot-backed securities. Physical AI becomes a general-purpose technology when other industries reorganize around it. That reorganization is the true trillion-dollar effect. The steam engine was not valuable only because engines were sold. It reorganized factories and transport. Electricity was not valuable only because generators were sold. It changed every industry. Computers were not valuable only because computers were sold. They changed information worked. Physical AI can reorganize physical work. That is the scale of the ambition. The transformation will be slower than a software release. It can be deeper. Factories, roads, and labor systems change over years. Once changed, they persist. The winners can enjoy long customer relationships. The losers can face long periods of stranded investment. This makes capital allocation critical. Build capacity too slowly and miss the market. Build too quickly and drown in unused factories. The leading companies will manage industrial cycles, not only product cycles. This favors experienced manufacturers and disciplined operators. It also creates openings for startups willing to take risks incumbents avoid. The final advantage may come from learning speed, not model training speed alone. Organizational learning. Can the company turn a field failure into a design improvement quickly? Can it update software without breaking safety? Can it communicate with suppliers? Can it retrain customers? Can it redesign manufacturing? Can it lower cost every generation? The company learning across the whole stack wins. Physical AI is a systems problem. The war is a systems war. One outstanding component cannot win alone. The stack must become an economic machine. This is why the phrase AI company becomes incomplete. A physical AI leader is an AI company, robotics company, manufacturing company, cloud company, service company, and finance company, or it builds an ecosystem covering those functions. The complexity is intimidating. The prize justifies the effort. The industry is moving from models that describe the world to systems that participate in it. Once machines participate, they generate feedback. The world becomes part of the training loop. Every object touched, every route traveled, every failure recovered, every hour worked. This produces a new kind of data economy. Physical data is expensive. It is also defensible. The company owning useful interaction data can build an advantage that text-only AI companies cannot easily copy. This may be the strongest moat of all. The body earns the data. The data improves the brain. The brain makes the body more valuable. This loop can produce the dominant physical AI platform. The first AI boom taught machines to talk. The next one teaches them to work. Talking creates engagement. Working creates economic output. This is why the physical AI war can become larger than the chatbot war. A chatbot competes for time and subscription revenue. A robot competes for labor budgets, equipment budgets, logistics spending, and production capacity. The money comes from larger pools. The costs are also larger. The winners need more capital. The failures are more expensive. The stakes rise on both sides. The physical AI war will not be won on a stage. It will be won on factory floors at 3 in the morning, in warehouses during peak season, on farms during harvest, in hospitals when supplies must arrive, inside machines that work clone enough for the economics to become undeniable. The final starboard will not show followers or demo views. It will show productive hours, cost per task, uptime, fleet size, customer renewal, safety, manufacturing scale. The company that leads those numbers can control a new layer of the global economy. NDIDID wants the computing standard. Google wants the intelligence layer. Tesla wants the integrated robot platform. Amazon wants the operational system. Boston Dynamics and Hyundai want industrial credibility. Figure wants rapid general purpose deployment. China wants manufacturing scale and cost leadership. Industrial incumbents want customer control. The battle lines are clear. The outcome is not. That uncertainty is what makes this a war. The trillion-dollar prize is not a single robot. It is the right to become the foundation beneath physical work, the chip beneath the model inside the machine, the software above the fleet, the marketplace for skills, the financing behind deployment, the data flowing back from every action. Control one layer and you build a business. Control several and you build a platform. Control the platform and you influence how the physical economy automates. This is the end game. Physical AI is not the moment when a robot looks human. It is the moment when intelligence becomes a standard input into machinery, when a manufacturer buys autonomy the way it buys electricity, when a warehouse adds robot capacity the way it adds cloud server, when a farm downloads a new harvesting capability, when a hospital deploys physical assistance through a managed fleet, when businesses call physical work through software. At that point, the technology stops being a category. It becomes infrastructure. The companies fighting now are trying to own that infrastructure before the rest of the world realizes how valuable it can become. The first trillion-dollar AI war happened in data centers and on screens. The next one is moving into the real world. And this time, the winners will not only control what machines know, they will control what machines can do.